Hi there, I'm Clément. This is the third video about how to generate random numbers in embedded system. As a reminder, we're using that nRF52 development kit that is using a Cortex-M4 microcontroller to generate random numbers on it. We are not using any specific hardware, just the standard boards that we are getting. And for now, what we've been using is some testing tools to actually quantify and determine how good or bad our random numbers are. And we've been using an ADC inside of the microcontroller to generate some noise and get some randomness. We've seen how we could get some different sources of random from different environmental phenomena that we could measure. All those techniques are extremely nice to generate real random, but that use a lot of energy, a lot of time, and we cannot always do that in our embedded system. A lot of those run on batteries, and we need to save those. So what we're going to see in that video is how to use a pseudo-random number generation algorithm to extend that randomness that we generated into something that we can use a lot more. So first of all, a word about pseudo-random number generation. The way to think about it is like a list, an algorithm that gives you a list that is always going to be the same of numbers that are not correlated to each other or that don't seem to be correlated to each other seemingly. And that list is extremely long, very, very, very crazy, super long. That's fantastic, and that means that when you get the next number, it's not going to be correlated to the first one in any way, shape, or form. Fantastic. But every time you start your microcontroller, you're going to start reading at the start of the list. So that's always going to be the same first number, the same second number, the same third number. Those are going to be random to each other, but you know that every time your microcontroller starts, it's always going to start by that first random number, then that second random number, and so on and so forth. So the trick about how to use pseudo-random number generation algorithm is to start within the list at a random point in it. So when you start at that random point, then the next one are going to be random, and if you start somewhere else, you don't know what's going to happen in any way, shape, or form. If you use that function a lot in your application for a long time, that would be a good idea also to jump at random point, and even better to jump randomly at a random interval of time at random points inside of that list. That process of jumping inside of that list of numbers is going to be called seeding the algorithm. In this application, we are in embedded system, so space is very important. We don't have much of it. Even though that microcontroller is really big, we still want to save space. In this application, we're going to use the Mersenne twister algorithm that seems to be extremely popular in computer science, and there is an implementation of it that is called TinyMT that you can get online. I'll put a link in the description. That increased the size of my application by 704 bytes in total, which to me, that'd be great if it could be less, but I got trouble imagining it being less. So we're going to see how to use it to actually generate more numbers, and we're going to measure how good or bad that random is. So there we are. As explained in the previous video, that function is called every time we get a sample from the ADC, and we're going to use that as a way to generate a first random number that is going to be used to define where we're going to start reading inside of the giant list of pseudo-random numbers that I was talking about before. So that first random number that we are generating is the seed here. That seed in the Mersenne twister that we're going to be using needs to be 32-bit long, knowing that each and every one of our ADC samples are around 5 bits of randomness in each byte. We're going to cut them and only take the 4 lowest bits inside of each sample. We're going to take 8 of them together to create an entire seed of 32 bits. That's what's happening. So we got 2 stages, the seeding stage and then the generation stage in our algorithm. We are just going to shift 4 bits, then all our samples, our new sample, and we're going to keep counting until we get our 8 samples. That means that our seed is full of 32 bits, and we can init our Mersenne twister. That's all that there is going to be into it, and then we can jump to generation. And every time the ADC gives us a sample, we don't really care of the sample in that case, we're just going to get one random number that is going to be 32 bits from the Mersenne twister, and we're going to display it. As before, those are displayed on the serial port, and then I got a small Python script that's going to convert it into a binary file, and then we can run the proper statistical test on the results. Let's see those results. Each and every sample from the ADC, we are getting 32-bit from the Mersenne twister. So that means that we're getting 4 times more samples than what the ADC is giving us because of the structure that I designed there. That means that we're generating a lot more data than before that. So at least our numbers, our statistical numbers are going to be a lot more representative of the true randomness of that entire application. We are 25,000 samples, so I can stop collecting data and we can run our analysis. And there we got our result. First of all, entropy. We got 7.99 bits per byte. That's amazing, almost perfect to 8 bits. The chi-square, that is one of the most sensitive tests. That one, to be considered as good, should be between 10 and 90%. We are at 36. Fantastic! Exactly what we would want. Arithmetic mean, 127.6. Almost perfect. Monte Carlo value for pi, we got 0.67% of error. A lot better than what we had before. And the serial correlation at 0.001. Amazing. Still some serial correlation, but a lot less than what we had before. The Mersenne twister allows us to actually get some seemingly fully random numbers. Remember that if you don't seed it properly, your microcontroller is going to reuse the same series of random numbers each and every time you restart it. So the seeding process is extremely important in our case. And remember to reseed from time to time when you're using it a lot. There you have it. An example of an algorithm that is actually fairly small in size, that allows us to extrapolate some true random numbers that we got, but we making it a lot simpler, a lot lighter when it comes to processing power, and so a lot more efficient regarding energy in the end, compared to collecting data from the external world. That's it. I hope that helped you, and you'll have all the link in the description to rebuild that on your own at home. See you! No funny. Robot? I'm not a robot. Beep boop, beep boop. That's racist based on my name. You're saying robot because my name is Roblot. Do disco robot, do disco robot.